at least 50.
At least 49.
Greetings and welcome, friends, shareholders of all stocks of all ages, and people who maybe have majority share. I think that means you have to own 50% of a company. I imagine that if you own that much money, you should maybe fund my YouTube channel. You know, subscribe. Is that how it works? No. I guess subscriptions are free. Well, you could maybe play a commercial, request it to be played during my YouTube videos, or preferably at the beginning. Well, anyways, today we're talking about rectangular and parametric equations of conic sections. That's right, we're combining our concept of parametric and our concepts of conics together. So instead of just having an object moving along a straight line path or an object moving along a parabolic path, which we did with modeling motion of projectiles, now we could have an object moving along a circular path, say like an electron. All right? Or we could have an object moving a parabolic path like, projectile. Or we could, have an object moving along an elliptical path like a planet around a sun, perhaps, where the sun would be at one of its focal points, by the way. Or they could travel along a hyperbolic path, which does anything do that, guys? I don't know. Well, anyways, so for starters, this is just some recognition capability that I'm going to teach you real quick about general equations for conic sections. So here's general equations. This bxy term, we didn't do a lot with that. That was only for rectangular hyperbolas when they were kind of skewed at a 45-degree angle. But we'll actually see that a little bit later on in this course when we revisit that section as well with rotations of conics. But general equation of conic sections looks like this, and where A, B, and C are not all 0, but maybe some of them are, right? That's fine. So in terms of classification, a circle occurs whenever you have both A and C being equal, positive or negative. I also happen to write down the standard form for the equation of a circle right there, center HK, radius of, that actually 1 should be an r squared. That should be an r squared. Bam. There we go, of radius r, right? So a circle you can recognize from general form whenever the squared terms have the same exact coefficient. All right? That's similar to an ellipse, if I skip over there, where A and C have the same sign, but A is not equal to C. Okay? So if they're 5 and 7, they're both positive, it's going to be an ellipse. Hyperbola occurs whenever A and C have opposite signs. All right, so similar to an ellipse. And you might remember, I won't go into the definitions of ellipse and hyperbola, but there were some similarities there and some differences. Oh, that's so hilarious for anyone who'd get that. Well, moderately. Nah, maybe not. Well, anyways, and it's a parabola anytime A or C is 0. And the reason that it's a parabola when that occurs is if A or C is 0, we'll think about the fact that we'd only have one squared term in those cases, and notice that in standard form for a parabola, there's only one squared variable that would come out of that. So, so that's how we could kind of do some quick recognition. Also, I drew some little pictures here, just so you remember what those look like. So for our first example, it says identify the conic section represented. So looking at this, what type of conic do you suspect that is based off of our information? Well, there's only one square term, so this is actually a parabola because there was no x squared term to match it, right? So A or C was equal to 0, so it's a parabola. The A was, since there was no x squared term. All right, so check this out. Here's another one. So my A would have been, I guess, technically the -2, and the B would have been +3. Their signs are different, so it's a hyperbola. And also I would have immediately known that it wasn't a circle because the numbers were different themselves, right? What was the question?
Why is it not hyperbola?
Because A and C had opposite signs in general form, right? So our squared terms, one was positive and one was negative, right? For this one here, all right, they've got the same signs, they're both positive, but their quantities or magnitudes, I guess you could say, are different. So that's going to be an ellipse. Oh, they are perfect squares. Probably just because it comes out nicer when we put that in standard form later, which you don't have to do right now, so you're welcome. And this last example, notice that A and C not only have the same signs, but the same numbers, so it's a circle. Yay, circle. Hooray. So that's the first skill that's taught in this section, but let's get to the meat of this concept here. That was just freshening us up. Freshening, it was making us more fresh. We were fresher. Yeah, as a result of looking at some of those. So it says, graph the curve defined by the parametric equations x equals 4t squared and y equals 3t, where t is between -2 and +2. Then identify the curve by finding the corresponding rectangular equation. Ay caramba, am I right? So here's my two parametric equations, x equals 4t squared and y equals 3t, right? And I'm going to make a little table of values for t, for x, and for y. So, and since t happens to be going from -2 to +2, I chose my t values that are going to be nice for me. So let's fill out this table. Let's work with the x first. -3t, so 3 times 3 times -2 is -6. 3 times -1 is -3. 3 times 0 is 0. 3 and +6, right? Touche, my friends. So, yep, that's the thing. Good save. I was trying to choose the friendlier one first. All right, negative for x now. -2 all squared is +4. 4 times 4 is 16. Plug in -1. -1 all squared is +1 times 4 is 4. 0 squared is still 0, and multiplying by 4 does not change its zero-acity. 1 squared is 1 times 4 is 4, and 2 squared is 4 times 4 is 16. So, if I wanted to graph this, let's see, what sort of grid am I looking at? I'm going to go at least as far as 16 on the x-axis and as low as 6 and as high as 6 on the y-axis. It looks like on the x it only goes as far as 0, right? To the left. Let's see. Oh, that was weird. So, there we go. Now I got my snapshot. So, I'm going to make this little grid here. And so, I'm just going to plot these points. So I've got my x and y's. Notice I chose my kind of locations wisely. And not only am I plotting the x and y, but I've got to take t into consideration here, where I'm thinking of the movement of this object along this path. All right? So let's see. First point is over 16 down 6. So there's one point. That's where t equals -2 there. All right. Then I've got over 4 down 3. All right, so right there-ish. And t equals -1 there. And then I've got 0, 0, 0, 0. So t equals 0. And then I've got over 4 up 3. And then I've got over 16 up 6, like so. Right, and t equals 1 and t equals 2 respectively. So when I draw this, this actually fits a parabolic path. I'm going to draw this in this technique. It's technically not as pointy as I've made it look, like so. And what I would do is I actually want to not just know the path of the object, but also represent the motion. So we'll actually throw some little arrows on it indicating that it's moving like so. And actually, I just realized technically this arrow here and this arrow here would not exist. How do I know that? Actually, oh, even worse. The graph would have stopped right there and right here. How do I know that? What was the original problem telling me? Yeah, so this actually stops at those locations. Okay, so we could determine that the path would have continued on, but they only want us to graph based off of that restricted domain for t for those inputs. Okay, so you can see that the object started here and then moved kind of along this parabolic path, right? So now they asked a second part of this question. They said, identify the curve by finding the corresponding rectangular equation. Now that's actually not going to be as bad. And we technically, I think we did tinker around with this concept before. That if I wanted to find the convert from parametric to, actually, yeah, back then we were converting to vector equations or rectangular ones, right? What I'm going to do is solve for t in both equations and substitute. And then substitute. Right. So, for my first equation, x equals 4t squared. Actually, maybe I'm just going to write it over here, y equals 3t. That's what I'll do, make some space for me because I'm running out of room here a bit at the bottom of my page. So, if I want to solve this for t, I would start by dividing both sides by 4. And here I divide both sides by 3 for the y. Well, I'm using that color, why not? So I'll have x over 4 equals t squared. And over here I'd have y over 3 equals t. And what would I do to get this t by itself? Root, correct. And plus or minus, I wouldn't forget it. So t is equal to plus or minus the square root of x over square root of 4 is going to become positive 2 in that denominator. And now since both of these are equal to t, that means I can substitute one in for the other's t. Or you could also view it as some sort of transitive property. If this equals t and t equals that, then they equal each other, sort of thing, right? So I've got y over 3 is equal to plus or minus the square root of x over 2. And now I'm going to, I actually have some choices. I can try to put this in a couple different forms. I think none of my standard forms have square roots in them, technically. Oh dear, is it lagging out on me? Just a little bit. So yeah, none of these forms have square roots in them. So I'm going to get rid of that square root by squaring both sides. That sounds like a good idea to me. And that will give me y squared over 9 equals, I'll lose my plus or minus because either case that's going to become positive, over 4. And then if I wanted to say solve for y, I can multiply both sides by 9 because it looks like this is going to be some sort of a parabola since I only see one squared term. And so I'll have y squared equals 9/4 x. Or if you really wanted to be a fancy pants, you could write that as y minus 0 all squared equals 9/4 times x minus 0, where the 0, 0 vertex would be a little bit more apparent to us. So So yeah, so it turns out this is a parabola. Okay. Although technically rectangular form, I also would have accepted this over here if you just multiply both sides by 3. That's technically still a rectangular form. It's just not in standard or general form, respectively. All right, let's try to fit one more example in here, going the other way. So here's our last example. It'll say, find the parametric equation for the equation y equals x squared plus 3. And this will be similar as well to something we've done before. So what I'm going to do is just start off with an assumption. All right, this happens to be a parabola that's opening upward, regularly shaped. It's been shifted 3 units up from the origin. So I know this is a parabola. As far as the location of a point on that parabola at any given time, I just arbitrarily pick a time to go with it. All right, so to get parametric form of this, I'll just say let x equal t. And now to find the y, or vertical parametric equation, I'm just going to substitute t in for x. So I'll get y equals t squared plus 3. And actually that one's already solved for y and everything. So those would be my 2 parametric equations, and nothing too crazy. And that's it. And I mean, technically, if you wanted to graph this using the parametrics, you could make a table of values for t and plug them in, etc. Yeah. All right. Well, I'm glad you thought so. Well, thanks for watching, Internet friends. Bye-bye.